Myself, Krish Rathukar, very warm welcome to all. And today is Mathematical Foundation Day, where we will focus on that little bit mathematical concept around artificial intelligence, and this is an important one. Okay, and this is important part because of that when we in this particular one we covered the Hessian matrix, and this is the important one. Okay, after the Jacobian matrix. Jacobian matrix is just as a different from it's just find out the sensitivity of input and outputs, like at the bulk amount of the input and bulk amount of the output. If you just find out this both about sensitivity of both of them, then I think like Jacobian matrix is best for it. But when you actually want to know that how can your model, how actually your model perform, and actually when you're moving from the step by step to back propagation and something, all the particular step. So really, Hessian matrix is important one, and let's try to understand first. Okay, so initially we understand this Hessian matrix with their I think like there is two view of their Hessian matrix. The first is geometrical view and second one analytical view. I think geometrical views want to say like how actually the curvature change. For example, let's suppose this is a graph, and I think like there is a parabola, and if you just find out the slope, how actually slope change here, and how this particular stuff is banned in their directions when they actually try to move. So in that particular part, like when you just where is a curve part, where is the local minima, where is a flat part, if you just find out if this is the let's suppose this is a flat part, and how actually the model know this particular stuff is the flat. Okay, so when we actually focus on geometrical view, then flat part, if you want to just know that where is the flat part and how the flat part is, then I think like Jacobian matrix helps us, I think Hessian matrix helps us to know the status of the curvature change, like how the curvature changing when the actually data moving step by step. So that's the basic geometrical view. When we're talking about analytical view is all about like how actually the particular data, like sensitivity change. It's all about like in Jacobian matrix, we discussed a little bit about bulk amount of function, bulk amount of inputs. Like you can say all the particular input function and output function. We just find out the sensitivity of each other respectively. We get the number and matrix which show that how input and output are sensitive to each other. So that's the basic difference between both of them. Like in that part, we actually focus on sensitivity, and in that part, we actually focus on how actually sensitivity itself change. So that's the basic thing that we're talking about in their Hessian matrix. And Hessian matrix is just only for curvature change, how actually the parabola change when actually moving toward their different data points, uh, like moving toward the different data points, and sensitivity change and second order partial derivative. So here we actually focus on the find out second order partial derivative, not at first order partial derivative. Because of that, we actually find out the sensitivity of change. So the first we need to find out the first order partial derivative, Jacobian matrix, then after second order partial derivative. So that's really helpful for us. So that's all about it. And I'll try to connect this particular one with the real world concept, how actually it's work. But okay, so let's start with first. Okay, so let's suppose you are driving a car, and I think like you are moving to downhills to uphill. But in lots of like after few like when you actually driving a car, you like you analyze that, you know that we need to adjust the speed. Okay, so in that particular speed, we need to adjust the speed and we need to accelerate the car according to their ups and down in the hills. Okay, so we actually need for understanding where is the ups and downs in that particular hills and the status of the ground. Okay, so sometime you need to accelerate much more, because of that there is a up ground, and so that's why we use this particular stuff which is called Hessian matrix. Hessian matrix helps us to know where is the ups and down, and they tell you like where to increase the speed or where to reduce the speed. Okay, especially that's the all about the fact that we're looking for. And when we actually focus on Hessian matrix, this is a simple way to discuss about like how actually speed increases and how the speed will be decreases. So that's the basic thing we're talking about. And oh, okay, so little bit confusion in here, like Hessian matrix and gradient descent. And gradient is all about pushing your particular weight and biases to that. When you actually try to train your model, gradient is all about pushing your model to adjust the weight. Okay, increase your weight. And gradient descent is all about reduce the weight to minimizing the loss, okay, to improve the accuracy. But Hessian matrix is such a different case. Hessian matrix only help you to know where is a flat and where is a sensitivity change, how the actual sensitivity change. So you need to adjust how much the particular stuff in your learning. Let's suppose if your model want to try something to learn, but if they fail to learn, but where to just we need to just accelerate the changes, okay, where to accelerate the changes to achieve that particular milestone of the accuracy that you want to. So let's suppose if you are not 98% accuracy, then I think it's in that particular one, Hessian matrix help us to know that how much you need to accelerate and which part you should to accelerate in that entire data landscape, and the entire dataset landscape to just achieve that particular milestone. So it's give a real time status of that, what the status of the data is, and where to accelerate the learning, where not to accelerate. So that's the basic pathway of Hessian matrix. So Hessian matrix is similar like this. And when you're talking about the key properties, and is this is the basic mathematical formula, which is I think this is not a formula, but you are going to just find out this according like this. So this particular key properties of the Hessian matrix, like symmetrical, and if the mix or partial symmetry, like if the mix partial derivative, okay, then I think like this both are symmetrical in case like Calrod's theorem states that the both mixed one is like symmetrical in phase, okay. And it's also help us in optimizing local minima and local maxima, and help us to know that where is the minima point, where is the maxima point, and after this particular stuff. Okay, so that's the Hessian matrix want to say. And local minima and maxima are really helpful for the model to adjust weight according to it. So that's the basic thing. Okay, so that's all about the Hessian matrix. We have covered lots of concept around the Hessian matrix, and just remember Hessian matrix is only for if you just look toward this, there were two views in their particular Hessian matrix. I think like there were two images of their Hessian matrix. The first is like geometrical image and analytical image. Geometrical image says that how the actually curvature change. It's know the what the status of curvature is, and second one is like you can say analytical image of the particular Hessian matrix is like how sensitivity itself change. So that's all about it, Hessian matrix. So again, if this one is going to productive for you, if you learn something from there, then it's my pleasure. See you soon.